Well, welcome. This is our April side session where we're going to discuss a little bit more about certain aspects of the structural modeling context. It's kind of a brainstorming session, so I'll just kick some ideas around. And the first thing that I'm going to talk about just briefly is the concept of the art, the abstract relation type, and how that relates to the AMEI, or the Augmented Model Exchange Isomorphism. The fundamental idea of the abstract relation type is to focus on the structuring relationship that creates a system. It is patterned after a computer science concept of abstract data type, where you have methods and procedures and a formal structure through which you communicate certain functional forms and behaviors. So the abstract relation type itself takes the three language components that were proposed and outlined by Warfield and uses those and provides a framework for those and a way to actually document this relationship, the natural language relationship that creates the system using the abstract relation type. So it's a formalized concept to address, document, and communicate the natural language relationship that creates a system. However, in the abstract relation type itself, it doesn't need to be complete in all the areas. So you can have a graded approach. It has a prose section, it has a structured graphics section, it has a mathematics section. In the prose section, you can either have formal prose or informal prose. In the structured graphics section, you can have formal structured graphics or informal structured graphics. And in the mathematics section, of course, you have formal mathematics because mathematics is a formal language. But those specific blocks and components in the abstract relation type, they all don't have to be filled out for it to be useful. And if you're familiar with UML, a lot of people use UML structured graphics, just the icons, as a sketch language. So that's using a more of a formal language informally. And so you can use sketches and so forth in the graphics part, or you can use structured graphics that flow from the graph types that are associated with matrix math. There's a wide range there. The Augmented Model Exchange Isomorphism is a special type of the art because it requires that you have formal prose, formal structured graphics, and of course the mathematics, and that those have to be isomorphic. And so that you take a natural language structuring relationship, you look at it, and that once you have it in the AMEI, there's another requirement that each one of those forms, those language forms, are isomorphic with each other. So I think I'm going to stop the brief introduction there to the difference between the abstract relation type and the augmented model exchange isomorphism, and turn the session over to Kevin, have him lead the discussion on the other components. Kevin,
okay.
You're on.
Okay. So we're talking about mapping the natural language to mathematical properties. And when John Warfield was working with Frank Harari, the mathematician out of, I think he was University of Michigan. They were concerned with relationships that were transitive. And then in most of Warfield's work, he was addressing relations that were partial orders. And much of this chart are partial orders. The way he's listed the spatial ones are not partial orders. But I think most of the rest can be viewed as partial orders. Nowadays, I think the thing to be concerned with is existing modeling formalisms like UML or SysML, object-oriented modeling, which uses a combination of relationships. So let's just take the simplest view of object-oriented modeling. It has part-whole relationships. It has class hierarchies, which are a similarity relationship. And it has a functional relationship, which is in the methods of an object-oriented model. And it's not clear to me which relationship on this chart is the part-whole relationships.
Kevin, can you go over that again with the methods? Let me take a note on that, because I'm not that familiar with the computer science worldview. So I need to take notes as you go.
Okay. Yeah, so in, let's say in the Rumbaugh, one of the early approaches to object-oriented analysis, there's three basic relationships that they modeled. They modeled part of relationships is something a part of something else. The more common thing that, the more common relation that object-oriented modeling is known for is the class relationship. Is something a type of something else? Because they're interested in reusing software. So if they can understand if something is similar to something else, they can reuse that something else. And so doing class hierarchy is almost synonymous with object-oriented modeling. And then to talk about the relationship between two objects, that's usually in what was in the Rumbaugh techniques called the methods. Also can be viewed as an attribute in one object being calculated based on an attribute value pair in another object. But it's about the functional relationship between objects. So those are the three basic relationships in object-oriented modeling: the part-whole relationship, class hierarchies, and functions. Functions are a partial order. If a function is not a partial order, it's not a function. That's a pretty well-defined one. Part-whole relationships are not as well-defined as functions. And there are, in the study of mereology or part-whole relationships, there are different notions of part-whole relationships depending on the specific relationship, like included in or part of. There's nuances to it. The class hierarchy, it's not immediately clear how that can be modeled as a partial order, but there was a debate in the realm of systematic zoology that went on for about 40 years of trying to determine the relationship that by which you could model taxonomies. What is the relationship that what is a transitive relationship that can generate taxonomies? This was a debate between systematic zoologists and mathematicians for about 40 years, which was covered in the Journal of Systematic Zoology, which I read through one summer. I read the whole debate. And this guy by the name of Nelson Goodman came up with the definitive answer. And this debate was called the problem of imperfect community. And that is, if you're trying to sort things, things have more than one attribute. And so if you try to sort things based on the similarity of attributes, you have this problem that it can generate multiple taxonomies. And what Goodman determined was the relationship that you ask that is transitive is A and B more similar to each other than C and D is similar to each other. And that comparison between 3 or 4 items behaves in a transitive way. So if you do it with A and B and C, this is basically how repertory grid technique works for to do personal construct theory, where it's called triadic elicitation. They found that this is interesting, that people can pretty reliably answer about the similarity of things if you ask them with 3 objects at a time. And you ask, one way to do it is to say, which 2 are similar and which one's different? And then they ask why, and that elicits a construct. But people can reliably come up with stable structures if you ask them 3 at a time. And so it happens to match the mathematical argument of Goodman of asking, is A and B more similar than B and C? Now, Warfield never used ISM to model class hierarchies, but I think this would be an interesting application. But I'm not going to get into modeling classes with ISM at the moment. That's not something that hasn't been done. But I think the two more basic things to worry about with modeling, using ISM to do something like object-oriented modeling, is part-whole relationships and functions of. And there's been a lot of work on part-whole relationships and functions are almost simplistic compared to the work that's gone on in part-whole relationships. So in part-whole relationships, this is a little twist on the wording that we've used, where they define it as reflexive, transitive, and anti-symmetric. And so everything is considered, in mereology, everything is considered to be a part of itself. I'm afraid that's going to drive Joe crazy. It's transitive if any part of a thing is itself a part of that thing, and 2 distinct things cannot be part of each other. That's the anti-symmetric condition. That's different. Anti-symmetric is different than asymmetry. This is how it's stated in formal logic. Are you with me?
Yes.
Okay.
Yes, that's good.
Yeah, Kevin, it's interesting, and I think that it's highlighting some areas where we would need to establish, standard interpretation so that we understood the implications of what's being said.
Yeah. Now, so this is the first, this is kind of a, this should be simple, right? But it's not simple because Warfield defines the partial order as being irreflexive, transitive, and asymmetric. And here, a part-whole relationship that is considered a partial order, they call it, they say it's reflexive, transitive, and antisymmetric. So kind of off to a rocky start. Do you have any, I know, Joe, in thinking about, for example, if you're modeling precedence relationships, that it drives them crazy to say an event is reflexive, that an event can precede itself.
Yeah, so this is very good to focus on these concepts. One of the things that we're doing right now actually is going through for next month and working on the properties associated with the these structuring relationships. And one of the things that we're working on, and it's kind of trying to discover an appropriate attribute, and one of the things that we're thinking about doing is calling it an attribute of alignment. And how well does the concept align with natural language thinking? And that's just very early on kind of ideas, but when you think of the idea of, in the mathematics here, that allows an event to precede itself, that does not align very well with our common understanding and experience. And so what we would do is we would say, okay, let's create some kind of definition for an alignment attribute. And we say, this is not aligned. This doesn't, even though you can say this mathematically, it really doesn't align well with our normal experience. But that's kind of where we're going with this kind of stuff. It makes sense?
Yeah, so how about this statement, everything is part of itself? How does that rub you?
Well, so the idea of the work that we've been doing is to go ahead and reduce complexity. And we reduce complexity by reducing uncertainty. And if everything is part of itself, there's some uncertainty introduced in that. Because when you're talking about, it's difficult to make a distinction between the object itself and the part. It overlaps. There's some uncertainty there. But if you say an item cannot be part of itself, then there's no uncertainty. So just from a functional standpoint for the definition, if you don't allow an object to be part of itself, then that reduces uncertainty. Does that make sense?
Yeah, it does, except, this isn't my stuff. This is Leonard and Goodman's. They kind of developed this over a period of decades to be a consistent logical system. And this is, I think in terms of implementation, it's more of, for the reflexivity, it just affects whether you're representing the identity matrix or not. So it's not that big a deal. It's more of a matter of convention. But I just think it's interesting that, on something that should be so simple that there's a difference in viewpoints on this. I don't think Warfield ever actually looked at the mathematics. The mathematics for part-whole relationships was pretty well developed by the time he was doing his work. I don't think he ever looked at it.
Well, I would just say that essentially our goal is to reduce complexity. We do that by reducing uncertainty. Anti-symmetry has uncertainty associated with it.
Yeah.
And basically, it appears to me anyway, that anti-symmetry, when we're dealing in the structural modeling realm, you eliminate that uncertainty by gathering empirical data. You go ask the question, is it this or that? So after some point in your inquiry, it's no longer anti-symmetric because you know the answer. It can't be both, right? So you eliminate that uncertainty in some more part of your process. And so those are the types of things that we just need to, develop a standard, kind of vocabulary. And we started out with the work that we're doing and just saying, well, right now we're not allowing anti-symmetry. Maybe later on we'll have to, but right now we're able to work around it and not have to use it. And in doing that, we eliminate the uncertainty and reduce complexity.
I think
Yeah.
I think one thing that would help is to, in the same way that in the AMEI, there is an articulation of formal statements, graphs, and matrices. On the other end, on the informal end, the rest of the art, it's probably helpful to articulate some a gradation or some the most fragmented natural language, diverse among modelers, to up to the level where you get things into some kind of at least semi-structured form that then can be brought into the logical form. Because I think there are several different scales within natural language. So before we get to what's formalizable, I think in ontology work, and in any kind of encoding, in any kind of formal encoding like object-oriented programming, there's already a lot of structure imposed, which isn't necessarily present in people's casual use of language, which is why we keep going back and forth between saying, the math view is so different from our natural language view. I think with the work of Peirce and SOA, talking about how symbols grow, natural language is a living system. So it can't be completely formalized without losing its living character of changing itself. So ambiguity is an essential part of natural language. I'm trying to say too many things here. I hope I'm making sense. I think that at one end of the art, one should tolerate ambiguity and inconsistency and whatever, throw in all possible ways that people use natural language. Then have maybe a middle ground where you have some kind of structure and consistency, for your given purposes. And then when you bring in ontological issues, you're constraining the use of language based on your understanding of how the world works or how you want the world to work. I'll turn it over and see if anybody understood that or not.
Well, Jan, I think that makes a lot of sense. On the formal side, what we normally do is use that formal logic to eliminate the need to spend resources to go ask the empirical questions and get the empirical data to resolve the uncertainty. And so what we really want to do is have on one side, on the formal side, mechanisms where we can use computation to minimize the amount of resources it takes to reach a solution. Where on the other hand, we have to just go get data and get empirical information and figure it out. And in between those two is an area where we need to use different approaches. And I would just point out that Dave Oliver and the folks that did the basic work to do at SysML, they really addressed a lot of these issues that Janet talked about and a lot of the issues that Kevin talked about. Dave wrote a book. It was interesting. If anybody familiar with Hartmanis and Stearns, who did the work on complexity reduction?
No.
Hartmanis and Stearns, they did the original work on complexity reduction and computation and time frequency related to real time, actually real machines. And they also did the object modeling group, object modeling process. Both those guys worked for Dave when he was at GE. And so there's some really good work that was done by that group at Nkosi. And it's the same type of concepts, were addressed. And I'll see if I can dig up some of that. I think Dave's book's available in PDF and some of the other work. But yeah, I think that would be a good step. I'll make a note to do that.
Okay. Well, one thing I think, following your using the formal side to shortcut using computation, the need for work on the empirical side or the informal side, I think that is the resolution of this issue of can something be part of itself? On the formal side, there is no interpretation. It's just a formal. You either use one set of axioms or another, and you just make sure that it's used consistently. And then when you reinterpret it, you want to use your debug trace, your trail of how you got to the formalism, so that you can get back and communicate with people on the informal side. So I don't think we need to worry about the fact that if people were looking at the math and saw that the computation was set up to say that something can be a part of itself, it would disturb them. I don't think we need to worry about that, because that's only as long as there's a trail coming, of showing how you got to that, and then you either added the identity matrix or you defined partial order in a certain way. That does not need interpretive coherence. It just needs formal coherence and a consistent trail back to interpretation. Does that make sense?
So, yeah. So what matches better with, I think, Joe's inclination and how we think of strict partial orders is what's called proper parthood.
Right.
Which is irreflexive, asymmetric, intransitive. So,
which may or may not be useful in the particular computations that you're doing. So on the formal side, you have various mechanisms available, but yeah, okay, go ahead, Kevin.
Well, the notion of parthood as distinct from proper parthood is part of when has to do with these guys' logical systems and how they derive their axioms and so forth. So there are some people's mereologies that insist on starting from proper parts, and others say they want to start from these more general notions of parts. But anyway, for what we're doing, this is proper parthood, I think, is more along the lines of how object-oriented modeling works. But surprisingly, people didn't do good math on object-oriented modeling. It only came years and years later, after the formalisms were developed, where people actually started worrying about the math and the logic of object-oriented modeling.
Right, and I think that's partly because I think that's been the case in a lot of fields, because people weren't articulating the difference between the natural language interpretation and the formalism, and the need to maintain the isomorphic mappings between those, or whatever kinds of mappings you could maintain. But because they didn't articulate the difference there, they didn't apply the consistency standard of formalisms to the formalisms, because they thought of them as sort of hybrid formal informal statements, I think. Whereas Robert Rosen's work, a lot of his insights came from his own mathematical background, where he separated the, as Warfield did, the natural language interpretation from the formalism, and said the key thing in the modeling relation is the isomorphy between them. But that very simple step allows you to use mathematical or the formal methods on the formal side, and the informal interpretive coherence on the natural language side, and use your identify standards so that you maintain coherence between them. That's the key thing that becomes necessary and possible. Because I feel like we're still concerned about interpreting what kind of partial order we're talking about. We're worried about the natural language interpretation of that, and that's only a concern when you're mapping back and forth between the two worlds. It's not a concern within the formalisms. The formalisms are a tool set that are available to you. That I guess the analogy is like non-Euclidean geometry. For millennia, people felt like geometry had to make sense. It had to be consistent with common sense experience. Then they realized, no, the formalism of the geometry can use different assumptions for the parallel postulate, and you get a perfectly consistent geometry out of that. So geometry, at that point, the math was sort of separated from our intuitions, which on the one hand makes it more powerful, on the other hand adds in an additional step where you need to explicitly maintain coherence between the math and your what it is you're trying to model, right? So the math is set free to use any kind of axioms rather than just the ones that make intuitive sense to us.
Right. Well, the sense of parthood isn't completely covered by the relational properties of a partial order. You need additional relational properties to designate parthood. And this is a kind of a quandary. I haven't figured out how you accommodate that in in the matrix modeling that we're doing with ISM.
Well, I think,
don't-
can I jump in here? Because I think this is a really
Yeah.
key point, is that you're saying you want ontological constraints, which is, these are your, yeah, and this is key, and this is the important part, I think, is that in the math, the part-whole relation in the math is too sparse, or it's impoverished compared to what people know and mean when they talk about part-whole relations in the in the natural world.
Right.
So that's where one tries to come up with ontological constraints to capture those additional intuitions about parthood. Right. So those need to be added to the pure math, which is just taking whatever statements you come up with and saying, here's a matrix, here's a graph, this is how they're related. The mathematical relation properties are too impoverished to capture the, they're not going to point the way toward the ontological constraints. You have to, you have to add those in. Yeah.
The way, I mean, we're using this system with groups of people. So the way you have to add those in is how you communicate to people about what you're asking them.
Right.
And that the math only captures part of it.
Right.
And there's, in the work on ISM, there's really nothing written about how to do that.
Right. That's why I was hoping this whole project could zero in on that question. I guess that's what I see this secondary project as needing to address, that's related to, but outside of what Joe and Mary are already covering.
So I had suggested that there are a few things that we can do in the math to capture these additional relational properties. Let me bounce through a few of the slides and see if I can find where that is. But for example, the decomposition principle of supplementation is an additional property. Right? Does that make sense to people?
Yeah, so I think what you're saying there is there needs to be at least two parts.
Right. There's got to be at least two parts.
Are you showing your screen right now?
Yeah.
Yeah, 'cause I see just myself. Now it's raining hard here, so it seems to think that I'm controlling. I don't know if that's because it keeps hearing me speak. Let me see if I can do something.
Janet, if you have the icons up of the different people that are on the call, if you click on Kevin's, it might delay that.
I just discovered that. Thank you. Just as you were saying that. Yes, that helped. Okay.
Okay, so there's got to be at least two parts. That's straightforward. So there's like 17 different mereological systems, depending on the axioms they use and how they derive them. So this one called the minimal mereology has these four relational properties. So if you just in the way that you run the ISM, if you just don't allow there to be a single part, then you basically have implemented minimal mereology. Let me just skip over that. these are kind of logical subtleties in mereology. So I'm going to skip over these.
Kevin, could you
Yeah.
go back 2 slides?
Here?
Right there. So can you briefly talk about this hash diagram and what it, I see there's a reference there.
Yeah. This is a diagram that represents whether one theory includes the axioms of another theory. So what we were talking about, we started with defining a proper part and then added weak supplementation to it. That gives you minimal mereology. That's all that's all we've talked about so far.
Okay, so the M down at the bottom, then that's basically the minimum mereology, and then you add like AM and ACM and AGM. Those are different.
M is ground mereology.
Okay. Partial order. And then
It's a partial
MM
order.
is,
And if
yeah.
you add weak supplementation principle that there has to be more than one part, then you
Right.
you get up to minimal mereology.
And I was just looking for the MM, and I don't see it on the chart.
Yeah.
It must indicate it by something else. Okay, good. Thanks.
Yeah. So as I'm whizzing by this, I'll just mention that Warfield didn't write too much about part-whole relationships, but he kind of implied that the inclusion relationship handled part-whole relationships, and it's different. So is set membership, and they're similar notions, but they're mathematically distinct. And I don't have a clear grasp of why that is. I'm just going to skip by to look at my recommendations on what to do for ISM. So here, the way to implement proper parthood with ISM is to never allow a question, is A a part of A? And if you don't allow that, and it doesn't matter how you implement the matrix, whether you have the identity or not, it's just a convention. To implement asymmetry, don't ask if B is part of A, if A is part of B is already confirmed. Now, one of the tricky parts with working with natural language is if A and B are different words, but they're synonyms, whatever you're modeling, like even an influence relationship, if they're synonyms, they'll tend to, people will want to confirm a relationship in both directions as a matter of kind of implicitly saying they're the same thing. So another way to put that is to implement proper parthood. Don't ask about things both ways on a diagonal, and don't ask about the complement across the diagonal. So these are.
Yeah, to what extent, I don't, so not having seen one of these ISM sessions, to what extent does one decide ahead of time how you want to what constraints you're going to impose like this, or does one just, aside from efficiency, as Joe said, doesn't one just want to ask all of the questions and then allow the system to identify issues that need clarification? Would you ever actually refrain in order to try to guide people into defining something asymmetrically?
I'm not exactly sure what you're asking. I mean, the goal of using ISM is to reduce the number of questions you're asking.
Okay. So I thought the goal of ISM was to elicit a model from the participants, but I understand that's so that reducing the number of questions is related to what Joe said about using computation for efficiency. So I would think, so you have a trade-off between efficiency and effectiveness here, because if you, especially that the idea of implementing asymmetry by not asking about B influencing A if A influencing B is already confirmed, that seems like efficiency might be stepping on effectiveness, because it might turn out that people might have said A implies B, but then, or A influences B, but the other relationship, the other direction might be the more important one, or they might, there might be a cycle, or so here deciding on
if they are the same thing, then it'll show up as a single part, which violates the supplementation principle.
Well, what if they're just in a cycle, not being the same thing? You mean, I would think that a lot of things,
Symmetry principle.
What's that?
If they're in a cycle and it's a part of relationship, it violates the anti-symmetry principle.
Right. I guess, so you're saying that so could you explain to me, I keep picturing, Cyprus and the Israeli-Palestine issue and it's hard for me to imagine an example where you're trying to do a part of modeling. So could you give an example of where you would be using ISM for part of modeling?
Like if you wanted to do object-oriented modeling.
Okay, and are you thinking that would be in a group modeling case?
Well, it's, I haven't seen it done.
Oh, okay.
I'm suggesting that this is a way of doing collaborative modeling.
Yeah, so Janet, I think that there's a number of places where this type of work is very important, especially when you're doing large-scale, complex system design. And I would say that in my experience, like when they did Deepwater, when redesigned the Coast Guard, the idea of what were parts, what organizational parts, what equipment parts, what functions that those organizations and equipment parts played were very important. And there was a lot of them. And there was so many, actually, that you weren't really able to manage all the detail between them. And this type of approach would take care of the details. So there are places where this type of approach would be very helpful.
If you think of like a bill of materials or like an assembly list and sub-assemblies, like something you have to assemble at your home, have assemblies and sub-assemblies. Not everything is related to everything else. It's a sparse matrix. And so the value of ISM is to not ask things that you can infer.
Right.
Right. Now, if you're modeling influences, we would ask in both directions.
Right.
We do, and that's how you come up with cycles, but that's an influence relationship, not a part of relationship.
Right. So I think when you're, so the example that you gave about parthood and sethood being similar but different, and then the different kinds of parthood that Joe listed, physical parthood, organizational parthood, there are ambiguities there that I would think, if you're just doing a physical system modeling, and so that if you know that, but the relationship between A and B holds in one direction, then it won't hold in the other, then you don't bother talking about it. If it's more open-ended, so that you have different kinds of part whole, then I have a feeling that you might still need to, that you can't assume that with the first answer is definitive. I guess that's what I'm saying, is that I would think that you would want the computational side to be able to flag issues and help you eliminate the ambiguities, but it just seems odd to me to say that the facilitator should infer things. I guess under certain conditions of stability and clarity and agreement among everybody exactly what it is that you're doing, and it's well defined, then you're having the facilitator sort of act as the computational system in cutting down the number of things that you ask about when you're on the empirical side.
Well, I would suggest this is done as part of the inquiry engine, not the facilitator, but
oh, I see. Okay, yeah, okay. So you're picturing,
if you say ISM in parthood mode.
Okay. In parthood mode so then you would need to, I guess the only thing you need to do is warn people that once they make a statement, it is taken as definitive, and as definitive of an asymmetric relationship, right? Or I guess if you're, so that they don't use a more casual sense of parthood than the engine expects. You would only want them to confirm the relationship if they truly knew that it held asymmetrically.
So, Janet, that's really a good point. And I think what Kevin and people that have done this work a lot and employing it is basically the idea that, and something that I don't know about, but I think would be a good exercise for psychologists and people that study the group interaction, is for any type of structural modeling relationship, if you could have a simple graphic model that helped to normalize all of the sensors. I mean, the people, what you're doing, you have individuals here that are providing the information. So you would want to have a simple set of models that you could get everyone to agree on. And that might help, normalize the sensors, so to speak.
Right. Yeah, this is all what Kevin is doing and what you're saying is all very helpful for me. It's illuminating. I hadn't thought of these issues like this.
Actually, this next slide gets a little more towards the mode that you were suggesting, Janet, where after there is a structure, then the software can point out that, for example, suppose people wanted to say A is part of B and B is part of A in both directions, okay? Then if we only ask one, if we only allow them to ask in one direction, then it's very likely that in the structure we're going to see something that has only one part, right? So
Right.
so then the software could suggest to the facilitator to ask, is there another object we did not yet ask about which may be part of A? If not,
Right.
then it's likely the A and B are synonyms. They're different names for the same thing.
Right.
And so that would be something to ask people, are they synonyms?
Right. This is more what I was picturing. Yeah.
Now, we usually don't run into that problem too much when we're doing ISM, because the way we practice it, we go through a process of similarity analysis and clustering things into similar categories. And if things are the same thing, they get identified before you even do ISM.
Right.
So that's just and the reason you do that is because you have too many things to conduct ISM with. So you want to reduce the redundancy that goes into the ISM, because it takes time to do, it takes a lot of group time
Right.
to do an ISM session. If you have 20 people in the room, which is a typical size, excuse me, and they're spending half a day doing ISM, that's 2 man weeks of people's time. It's expensive.
Mm-hmm. Right. Joe, what phrase did you use there about, you said normalizing the sensors?
Yes, so you need to have some type of process where you can identify, communicate to the group the normalized concept. And
Right.
there's some work that was done by the folks that did the software-defined radios, and they found that when working with UML diagrams and IDEF0 diagrams, that the same concept was very easily identified by the mechanical engineers as IDEF0s and by the software engineers in UML.
Right.
And that they almost had the two groups just couldn't understand the other things. So the guy went in and looked at this. I think he did his PhD in it.
Mm-hmm.
What he recommended was, well, IDEF0s and UML are both executable. What we need to do is determine these simple psychological tests of how people actually think about part, wholes, and relationships, and then simply use a computational engine to translate and present to these people the graphical construct in the way they think.
Mm-hmm. Mm-hmm.
And so to me, that's a little more advanced type of concept of using an interpretation of an executable language.
Right.
But we need to start normalizing and getting people to discuss these things.
Right. And those groups are also very trained to certain formalisms, so you can use that to communicate. And then there's an issue of people outside of, stakeholders or, business people or whatever who are maybe not trained to formalisms.
I think that if I remember correctly, the fellow was working with, people that were in charge of organizations. And so if a fellow was in charge of an organization and was going to use this particular equipment, and if he had a mechanical engineering background, then he would normally have this type of view of it.
Mm-hmm.
And if they had a software engineering background, he couldn't really understand or interpret the way this other guy did. And so they were really not dealing with the engineers themselves, but they were dealing with the higher level managers.
Mm-hmm.
And so these higher level conceptual pieces is actually what you appear to be working at mostly with ISM, right? Very high level, discover the system. What is this system? What does it look like?
So there's 2 more slides here. Here's a couple principles that take you into the higher mereologies. One's called extension. So if you have 2 objects that are composed of the same parts, they're the same object. So this is another example where after you do the inquiry, if you see something that has, if you see two objects that have the same parts, then you'd want to prompt the facilitator to see if they're really different or if they're synonyms. And then there's 2 more. There's another principle in mereology called composition or fusion or unrestricted sum. And that just implies a stopping rule that your inquiry is not considered complete until you've considered all the pairwise combinations. So that's straightforward. And then on transitivity, if B is reachable from A, then don't ask if A is reachable from B. Right, so that's looking across maybe a large expanse. So that's it. So having gone through this, what I saw is that there's to do part of modeling with ISM, you want a few adjustments to which questions are picked or not picked. There's some recommendations the system can make to the facilitator for 2 different reasons. You may want to ask if something is the same. In the case that an object has only 1 part, then that's probably the same thing under 2 different names, so the system could prompt you about that. And if 2 objects have the same set of parts, then they're probably the same, and the system could prompt the facilitator to ask that as well.
Mm-hmm.
And then I think that's it.
Yeah, very interesting. I hadn't gotten it all. This is very enlightening what you said there about the number of hours that it takes to do this and the dollars involved and the so I tended to picture this as just people sitting around variety of backgrounds trying to come up with a group model, sort of an open-ended thing, but you're putting the dollar constraints on it is very interesting.
Yeah, when you're doing this, there's a new question on the table every 2 minutes.
Mm.
And they have to decide within 2 minutes the answer to the question.
Mm-hmm. Mm-hmm.
And it's tiring. And when you work like that for several hours, white collar workers are not used to working on an assembly line
Right.
like that.
Right.
And they really get tired.
Uh-huh. Uh-huh.
They're used to letting their minds float around. Right.
Right.
Now, a whole nother realm of natural language mapping is the study of meronymy. And it is an example where an arm is part of a musician and a musician is part of an orchestra, but we don't use the notion of part in a way that means the arm is part of the orchestra.
Right.
So there are 6 kinds of part-whole relationships in terms of language use, and we've been on this for an hour already, so I'm not going to launch into this, but just to note that there's a whole study of natural language mapping to the part-whole relationship, which is beyond what I covered. Just was logic.
Right, but what you were assuming though was that there was some single case that you were dealing with, right? Because otherwise you do get into these the intransitivities and ambiguities.
What do you mean, a single case?
Well, that you're dealing with components and integral objects in your
Right.
yeah.
Yeah, that's the way I was talking about it. It was
Right,
as
that's right. So this is the next level of maybe we could talk about this next time, because I think it does get at what I picture would come up in open-ended ISM, where people would come up against these intransitivities.
Right.
Even with like defining an organization as is that a matter of the departments or the people or the you come up with similar kind of conflicts. Go on.
And I think that it's a good idea to try to keep these fairly close to an hour each. They don't go too long, and people can expect that they'll be about an hour. And if this might be a good place to break, and then as Janet suggested, do we want to set up a third, try a third Saturday of each month?
That's good for us, yeah.
Sure.
Okay, well, I'll set that up and send some stuff out, and very, very interesting, and we'll just continue to march. Thank you.
Okay,
Wait a minute.
Joe.
Before we leave, I've got a quick question, and that is, who is going to be summarizing these discussions and sending things out for review and so on?
I could do this one. I don't know
Okay.
about the next one. Okay.
Good to have you start.
Okay.
Yes, very good. Thank you.
Bye-bye.
Okay, see you on the May one.